Hi everyone, this is video 10 and today I'll be talking about mutual recursion and tree recursion, a continuation of the topic of recursion that we started last video. As I said at the beginning of this entire course, I'm going to make sure that I try to show you why the things that we're learning are useful. And one way that is useful in this case is that I'm going to introduce the idea of the Lund sum. The Lund sum is an algorithm for verifying the correctness of credit card numbers. And this is something every time that you input your credit card number online, internally, it does this automatically and checks that you didn't make any mistakes in inputting a number wrong in one place or something like that. So how does the Lund algorithm work? Well, you start from the rightmost digit and you move left, and every time you encounter the second digit, every second digit, you double the value, and if the result of doubling operation is greater than 9, you sum the digits of the product, and then you take the sum of all the digits. And if it happens that this sum, which is called the Lund sum, is a multiple of 10, then it is a valid credit card. So that's very broad. Let's look at a specific example to clear it up. So what I'm going to do is I have this Voodoo credit card number, and I'm going to go through from right to left. And the first thing I'm going to do is I'm going to identify which numbers I want to double. Well, I double every second digit. So this is every second digit. And now I double these and I copy the rest over. What was our special case? It should be the case that if the digit is greater than 9, we take the sum of the digits of that product. So here, the product is 16, the sum of digits of that is 7. Here, the product is 14, the sum of digits of that is 5. So that's our new digit in this place. And now, once I have this representation of it, I just straight up take the sum of this, and that is 31. So our Lund sum of this is 31, and obviously this is not a valid credit card number. And for those of you who are curious about whether this actually works, go ahead, once we write this function, or you can calculate by hand, go ahead and input your credit card number and see if it actually ends up being a multiple of 10. And I promise it will. And for those of you who don't want to do this, I'd be happy to take your credit card numbers and quote-unquote verify them, if you know what I mean. So, before we can actually go ahead and implement this, we had to talk about an idea called mutual recursion. And sure, many of you who have a knack for iteration by now could have seen a pretty easy solution to this problem. But when things get more complicated, it's important to see other possible solutions as well. And one thing I like about the mutual recursive solution to this is that it's very, very elegant. I think you will all have an appreciation for that. If not now, by the end of the course for sure. But anyway, mutual recursion occurs when two functions are defined in terms of each other. So let's look at a classic example of that. I'm going to define a pretty simple function, is even. And what this function is going to do is it's just going to check that whether a number is even. And I know that a very simple solution to this would just be return n modulus 2 is equal to 0. But I want to make this mutually recursive. Alright, so the way I'm going to do that is I'm also going to define a function, is odd. And with these two functions together, I'll create a pretty nice solution for is even. So, what's the simplest case of is even? If a number is 0, I know it's true that this is an even number. So I'm going to return true. And then otherwise, well, what do I know about even numbers? If it's an even number, it should be the case that the number before it is odd. So I just need to check if the number before it is odd. And in here, I'm just going to copy the same base case, just for consistency. If n is 0, what should be the case here? It should be the case that it's false. 0 is not an odd number. And then otherwise, I want to check, well, if a number is odd, I know the number before it has to be even. So it's the same idea. And there is our implementation of is odd and is even. So let's just test it real quick. Is odd on 5 should return true. Is odd on 10 should return false. Is even on 10 should return true, and is even on odd number like 15 should return false. So clearly this works. So let's analyze this a little more. The is even function is defined in terms of the is odd function, and the is odd function is defined in terms of the is even function, and this is the definition of mutual recursion. So now that we have an idea of what mutual recursion is, now let's implement lun sum. And to do that, I'm also going to bring back an old friend of ours, sum digits, which we defined in the last lecture recursively. So this was the recursive definition of that. Alright, so I know I'm going to need a lun sum function. And what this is going to do is I'm going to return the lun sum of a number n. And when we're working with mutually recursive functions, it's important to think about what things I want to work together. What are the two things that we have to do in a lun sum? We have to find the lun sum, we have to double every second digit. So what I'm going to also say to this function is that it's not going to double the last digit. So I'm going to pass it a number, and we know that it's not going to double the last digit to this lun sum. And this is going to be important when we define it mutually recursively. But let's also write our doc test first. Lun sum of a 12 is going to equal 4. What was the number that we did in our example? Let's quickly look at that. It was 1827634. 1827634. 82764. Let me just make sure. Okay, awesome. Okay, so this should return a lun sum of 31, and I also have a Voodoo MasterCard that ends up actually showing a correct lun sum that's a multiple of 10, being 20 in this case. And what I'm going to do, so now, how do we solve this problem? Well, one thing we know is that no matter what, when we're working with digits, we need to split digits up, right? So we're going to do that, use that same all but last and last somewhere. But let's first think about the simplest possible case. Let's say I have, well, let's actually look at the simplest possible case. Let's say I have the lun sum of a number 5. What's that? It's just 5. So if it's a one-digit number, I'm just going to return the number itself. So we've already done that type of logic. If n is less than 10, we just return n. Alright, and now in our else case, we're going to split the number up. So what we can do is we can just copy this entire line. Okay, let me copy that and paste it here. Oh wait, what did I just do? I broke a huge rule in computer programming. You never copy and paste code. If you can copy and paste code, that means that there's a chance for abstraction. Alright, so how can we abstract this? Well, the main part I want to get is this n divide floor div 10 and n modulus 10. So I can just write a function for that. Def split of n. And I can just return this entire part that I copied. Modulus 10. And this now lets me define this in terms of this split function, and it also lets me define this in terms of the split function. And by now you should see why this is a better version of this, because let's say I want to change the split sum function in some way. Everything else gets naturally changed too. So this is very important, because now we've made our functions more abstract, and that's very good. Alright, so now what do I have to do? Well, I'm not exactly sure, but I also know I need to do a lun sum. I need to also have something that doubles the next digit. So how can I do that? Well, I'm going to define a lun double function. And what this is going to do is it's going to return the lun sum of a number n, but in this case, it's going to doubles the last digit. So this will be the function that handles our doubling. All right. So what's the logic of this function going to look like? Well, I'm going to need to do the same splitting stuff. I'm going to take, so I'm just going to split the number. So again, this is why it's so useful. I don't have to write n modulus 10 and n florative 10. I can just write split of n. And now I need to have a doubled result, right? Because I'm doubling the last integer now. So I'm going to take my last integer and I'm going to double it. But if you remember, there was a special case of this. If it was a case that this was greater than 9, then I need to return the sum digits of this. And this is where we can use just the sum digits number, the function. So this actually takes care of this case. I don't need I could use an extra if case, but notice that if it's not greater than 9, then it's just the number itself, and sum digits returns that. So this is how we can use this function very easily. And now we have the same case. If it's the case that n is less than 10, or the n we pass into ln double is a 1-digit number, well, remember, regardless, we need to double that last digit. So we're just going to return the doubled value that we calculated. And then otherwise, well, now this is what we need to figure out. So when we're calculating the ln sum at the end, we need to sum all the digits together. So I know I'm going to have my last digit, and now I need to find a function that doubles the last digit and takes the ln sum of everything else. Well, what's that function? It's ln double. And so I pass in all but last. And now here, I have a function that doubles the last digit, and then for the rest of it, I need a function that just takes the ln sum of it. Well, that's great. I can take my doubled. So here, oh, I also forgot a return statement. Oops. Okay, return double plus what? So what's my function that takes the ln sum without doubling the last digit? It's that ln sum itself. And so I pass in all but last. And this, so now let's test this, should work. But let's just make sure. Python -m. Alright, it works. So now let's analyze this function a little. So, oh yeah, this was, so now we have the ln sum implementation here, and we have the ln double implementation. And the key reason this works is, remember, when we're calculating the ln sum, we are alternating between doubling digits and not doubling digits. Well, that's exactly what this mutually recursive function is doing. We first calculate the ln sum, we pass it into ln sum because we know the last digit is not going to be doubled. And then after we finish with the last digit, we know we have to double the last digit of the all but last variable, because that's everything but the last number. But that the last digit of the everything of all but last is going to be the second digit of the entire number, so we know for a fact that it's going to be doubled. So we pass it into the ln double function, and the ln double function takes care of doubling the last digit, and then now we know the next number doesn't have to be doubled, so we pass it into a normal ln sum function. And this is how these two functions work together to create the solution to this problem. And it's very, very elegant. I hope you have an appreciation for this type of code because it's very beautiful. I find it very beautiful, at least. And hopefully by the end of this course, you'll find clever solutions like this very, very cool.